So yeah, we're ready for chapter 12. I'm going to try to spread this out across 2 lectures like I like to do with the chapters from now on. That's my goal, at least. This one is pretty much, they could have made it part of chapter 11 if they wanted to. It's pretty much the same idea. We're testing hypotheses. We're going to learn a different method that's going to make a bit more sense for certain kinds of problems. We have some cool examples, some from the book, some from our data sets that we've been playing around with. And yeah, so please start reading chapter 12. We will talk about a new way of testing things. So yeah, this new way, or this new style of making a hypothesis test is called A/B testing. Have any of us heard of that? Because it is a computer science term technically. Like some people make a website. Like if you and your friend you log in on Instagram or something. One of you might have a new feature, one of you might not have a new feature, because they're testing it on just a small population of the users to see if it's good enough yet for prime time. That is technically called A/B testing. It's, I guess, slightly different than this, but same idea.
Kind of like when companies test it out in different certain cities, like how
Yeah.
Waymo with self-driving cars is in SF.
Exactly. Something like that. It's like that's the treatment and control. Remember those words. We'll get to that some more today probably as well. So yeah, good thoughts. So yeah, A/B testing is just like you've got 2 groups, Group A and Group B, and we have some data on each of them. We're going to compare the values. Like we've sampled people in Group A, people with some people who got the updated version of the Instagram app, the ones that were letting see the cool new stuff. And you also have some data from sample people in Group B, the people who have not gotten the update yet, or the people who we've not pushed it out to. We want to see like who spends more time on the app. Maybe that's the data we're trying to track or something, because we care about keeping people from their lives. So yeah, so the question in A/B testing is then like I've got these 2 groups. I've collected data, the same kind of data on each of them. What is there a difference? Did we make a difference doing the thing that separates Group A from Group B? So like do these 2 sets of values come from the same underlying distribution? Like we've got maybe a histogram. Ooh, why is that weird looking? There we go. Like I've got data from Group A. Looks like this. Whee. I've got data from Group B. It looks like this, maybe. I don't know. Slightly different. Whee. Something like that. It's like, is there a true difference is the question now, right? Do these sets of values that we're taking and comparing, do they come from the same distribution secretly? So maybe they look a little bit different, but maybe that was due to chance, right? That's our null hypothesis. So yeah, A/B testing in general is like we are answering this question by performing some sort of test to determine, were these groups really different from one another? Does this data imply that the thing we did to change Group A from Group B, the thing that differentiates the 2, like was that the cause of this difference, if there was one? So yeah, that's kind of where we're going. Same idea as last chapter though. Okay, so here is the silly example. Maybe not silly. It's a kind of a heavy example, but they took some data, and here are our example groups. We've got some data to play around with. So the 2 groups are mothers who smoked during pregnancy and mothers who did not smoke during pregnancy. I don't remember when they got this data. Hopefully it's not recent and you can't get a lot of this these days, but this used to be a thing, right? We didn't know the effects of smoking on pregnancy, but we took some data, okay? So that can be our 2 groups. We can have Group A being birth weights. It's like it ends up being the case, we will find that if you are pregnant and you smoke, your baby is going to be lighter when you have it. So that's interesting in itself. We're going to discover that with the data itself. So that's kind of weird, kind of interesting, kind of sad, I guess. But those are our groups. We've separated. We've got the same data. We've gotten the weight of the babies as they were born. And we've separated them into 2 groups. The groups that were born to mothers who smoked and the groups that were born to mothers who did not smoke. Okay? And so our question for A/B testing is, those birth weights, they look a bit small, look a bit lower for a certain group versus the other group, for Group B versus Group A. Was that just due to chance? We will find out. All right. Could the difference be due to chance alone? That's something that we could turn into a model and do a test on. Okay. So our null hypothesis is like, Yes, the difference was due to chance alone. Group A and Group B, they are the same group. Like the birth weight of a child does not matter on does not depend on whether you smoke or not, and so the distributions of those weights of the children are exactly the same. We maybe see a difference just because when you take random samples, or just like when you take a sample of a population, you see some minor differences, but that could just be due to chance. All right, so that's our null hypothesis. The difference really isn't there isn't actually a difference, and any difference that we do see in our samples are due to chance. If we sampled everybody, if we took an entire population, we took a census, then we'd find that there isn't a problem. So that's our null hypothesis. There is no difference. The weights are the same. We maybe just see a slight difference due to random chance, and that's something that we can generate and simulate and compare. And yeah, then the alternative is we say no to the null hypothesis. That's always how it works, right? It's okay, in our population, then the babies who were born to mothers who smoked, they ended up weighing less for sure on average than the babies of the mothers who did not smoke. So that is our alternative. And so if we're going to take some samples, we're going to run some simulations, we have to have a number that we're going to compare against each of the groups. So this will be our test statistic. That's the number we're going to generate as we do our simulations. It's going to be, let's make it be a difference between average weights of groups. So group B is the weights of babies on average. We'll take averages. The average weight of babies born to mothers who smoked, and then we'll subtract from that the average weight of babies for mothers who did not smoke. So that's going to be a number that we're going to be able to generate. And I hope you see, we think that B is a smaller number than A on average. So we should be ending up with negative numbers, right? If our hypothesis is wrong, if our null hypothesis is wrong, then we should get negative numbers because we think that more healthy babies they weigh more. Okay, something like that. Does that make sense to us? Questions about why we're generating that statistic. That's an important number because you have other options, right? You could have done the absolute value of the difference. That wouldn't really be helpful because it wouldn't tell you which one's lighter. It would just be a positive value at that point. You're not sure okay, was it A that weighed more or less? Because absolute value takes away the differences, the negative. We like that negative sign because it's going to tell us that, oh yeah, the A group weighed more than the B group if you subtract it in this way. You could have done it the other way, though. It's A minus B, and then positive values would be in favor of the alternative, wouldn't it? But if we run some simulations and we notice that this difference is very close to 0, then that is in favor of the null hypothesis. Does that make sense? It's all right, if there really wasn't a difference, we see just by random chance, we see usually it gets to 0, this subtraction gets to 0, then there really wasn't a problem. There wasn't any major difference between group B and group A. They were about the same, and so numbers close to 0 would be in favor of the null hypothesis. Numbers that are small, less than 0, good negative values, would be in favor of the alternative. Okay? And then we could be way off, and it could be in the other direction, babies born to smokers could weigh more maybe, but that's not really what we're going to see. Okay, so yeah, any questions about any of these words? Are they coming back to us? All these things, null hypothesis is just due to random chance, this is what happened. Really, it's the same among these two groups. Alternative is no, something else was the problem. One weighed less on average. One group weighed less than the other group. And so we're going to come up with a number that we can use in our simulations to figure that out. All right. So with that, let's read in this table, I think. If you'd like to follow along, I've made a new file, and our file name is called baby.csv. So if you'd like to find that one and read it in, go for it. I will do that now. So table, read table. We've got data/baby.csv. And I'll call that births. That's what the book liked to call it, I think. So here is a little bit of the table, the first bit. And so we've got a bunch of actual numbers. We're only going to focus on birth weight for this test and maternal smoker. So we've got birth weight is, I think, in ounces when the baby was born. So each of these rows is a baby born to a mother. And we have how long it took for that baby to come out to the world, gestational days. We have the age of the mother, the height of the mother in inches, the weight of the mother in pounds, I believe, and whether or not, true or false, the mother of the baby was a smoker. Okay, so we have all that data. We're just going to focus on birth weight and maternal smoker for right now. Okay, so that is how that's going to work. And so, yeah, let's, I guess, if we want to do it that way, let's just make a smaller table with just those things. I'll call it births. Dot select. Let's just select out the things we care about. We want maternal smoker. We can have that be first, and then birth weight, and we can have that table. We'll call that smoking and birth. I don't know, weight, something like that. Very long, but you can always press tab to have it autocomplete for you. So that's just fine. So now that's that smaller table. Those are the things we care about. Whether or not, for each row is a baby, whether or not the mother was a smoker, and then the weight of the baby when it was born in ounces, I believe. Okay, so I've got that table, and I guess now we should try to play around. So I have maybe some questions for you before we get to this slide. Yeah. Let's try to explore this data and try to notice that, oh yeah, the average group weights were a bit smaller. So here's a little crushed ice question for you. So first of all, crushed ice. Try the following things. Figure out how many babies were born to smoking mothers versus non-smoking mothers. So get like a count. So get the number of babies born to mothers who smoked and mothers who did not smoke. So that's step one. And then, once you know that number, those numbers, I think it would also be a good idea to get the averages. So among the smoking mothers, what was the average birth weight of the babies? Get the average birth weights of each group. So that is mothers who smoked versus mothers who did not smoke. Get the average weight of all the babies among the mothers who smoked and all the babies among the mothers who did not smoke. All right. I think that is good enough. Does the question make sense? So two different things we want to see right now. Do you remember how to do it? So I'll give you a few minutes to try. Please help each other. Say hello to the people sitting next to you and give this a little bit of a try, and then we'll come back. Because that's the first step. Is like we have to explore this data. Is like see which side we're on. Like, is there really a difference? Should we care about going further and doing a test? Let's see what our data looks like. It's numbers. What's the magic operation? I think you can use the same operation twice, just in a different way to get this distance. Baby.csv. Give you a few minutes to play around. Maybe make some graphs. It's like get it all set up if you can, so we can follow along. I'll give you a few minutes. And let me know if you have questions. So we need those numbers. I guess number one is like, was our sample good enough? Were there just like two mothers who smoked only? In that case, we don't get really a good result. And then number two is for intuition. Like how big of a difference, if there is one, among the groups? Really?
Yeah, one. Yeah, this was a little bit different.
Two things. All right, was that enough time, or I hear the clicking dying down a little bit? We get the average birth weights as well as the numbers of babies born to one group versus the other group. I will consult my notes and I'll give you another few seconds. That should be good. What about this one? All right. What was the magical operation that would get you these values? Did we figure it out? That could work, actually. You'd have to turn it into... Does it know false and true as, like, Python false and true? Or did it think of it as strings? Ooh, that's exciting. So we can birth weight dot column. Ooh, nice, it knows. That's amazing. So yeah, you could totally do count non-zero there. I honestly think that that would work. You could also do a grouping, because then it would tell you the other side too. I think that grouping was what came to my mind, at least. So let's do that. We got smoking birth weight dot group. If I just group by maternal smoker, or 0, either way, I'll type it out so that you can have that. Nice. We get a little count by default. It's like, all right, the number of mothers who did not smoke in this sample were 715, and the number of mothers who did smoke in the sample were 459. And so that's a decent size for each group, which is good. It's not just like 10 smokers versus 1,000 non-smokers, because that would be too small of a sample probably to give us any interesting information. So just intuitively, there are statistical things that you could do to say like what would be a big enough sample, but that's like to our intuition seems nice. And then if you go by default, it gives you the count. But you can also say after this, like, what do you want to do among those groups? What values would you like to pick out? And we can do an average, np.average among all of them. And so this gives us a wonderful little table where we can see, like, okay, the maternal smokers, the babies born to them were about, 10 ounces less on average. That's almost a pound, right? That's impressive. Or sad. I don't know. That's interesting, at least. So that means maybe we should run a test. That seems different enough. Let's see how this works. So our goal is to see how different these distributions are. And so you could draw, you could draw histograms now. You could be like smoking and birth weight. Let's see what those distributions look like right now. Give me a histogram on birth weight. But that's not good enough because that includes both smokers and non-smokers right now, right? That's not good enough. You could pick out, you can be like, you could select out only the ones where the maternal smoker is true and false, like dot where, do a dot where first, right? Dot where maternal smoker is, maybe we can do true first and false next, do a histogram that way. do a histogram this way. There's actually one other thing we could do, like do the false one. So like where it's true, give me the histogram. So that's the birth weight distribution of the smoking women, their babies. And here is the birth weight distribution of the non-smoking women and their babies. So you just have to like switch really fast back and forth to see if there's like a huge difference. It looks like there's a decent difference, whereas this one's a little bit under 120, right? This one's a bit over 120. So that's nice. That shows that there maybe is a true difference here. But if we go to the documentation for dot histogram, there's something cool that we could do here. Does it show it to us anywhere? Oh, it's a secret option. There is a secret option to histograms. It doesn't show us here on this documentation, so I won't test you on it then. But it's very useful for us right now. You can overlay histograms. That's what I'm trying to do right now. So I'll show that to you. Is it on this one maybe? Hist. Aha, this one does have it. All right. So alternatively, you can have, it's called group. If you say group equals something for your histogram, say group equals the name of the column that you'd like to group by first. Group by maternal smoker, get the values for this value, for like the true values, the false values, and then overlay them. So you can change the group argument. You can provide a group argument. So that's pretty cool. So let me show that to you. So instead of it doing it this way, we could say, give me a histogram for the birth weights, but first group by the column called maternal smoker, because that's the different thing, right? It's this one. Group by the different values of this column as you're making the histogram, and then it will overlay it. Oops. What have I done? Oh, thank you. Too many dots. That's kind of nice. You can see it right on top of itself with like some transparency. And you can see how like the maternal smoker equals true. It looks kind of like how it moved like a bin to the left for everybody. So that is useful knowledge, and that gives more firepower to our ideas. And like, okay, maybe we should really run a test now. Okay, so that's the goal so far. We've explored the data. We see that there is a difference. Now we have to figure out, we have to run a test to see, like, was this difference just due to random chance? That is our goal right now. Any questions about how we got here? Because now we're ready for the cool new stuff. So, all right, we have this knowledge now. Great. We would like to run a test to see, like, hey, which one is the best? Give me a p-value. Is it the null hypothesis? Are these values, when I create these statistics, like, are these values close to 0, or are they negative? Are they often quite negative? Because that will tell us, like, all right, that will give us firepower towards either the null hypothesis or the alternative. Was the difference due to chance, or was it due to something real? All right. So here's the trick that is going to be very powerful and nice, and it's something that we would have wanted to reach for last chapter if we had this knowledge. It's a very, very cool idea that I hope will make some intuitive sense. Here's how we're going to simulate the world under the null hypothesis. Because, like, in this world, right, we're assuming that the distributions were really the same. There was no difference between a mother who smoked and a mother who did not smoke, and how that influenced the birth weight of the babies. And so we need to simulate somehow. We can't just go and ask, like, we can't go and wait 9 months and, like, ask some women to smoke and ask some women to not smoke. That would be horrible. So, like, we can't go get more data. We have what we have. We have to, like, somehow sample from what we have and generate these new universes, right, under this null hypothesis with the data that we already have been given. Okay, so that's important. And here's the key, cool, secret fact and idea that I hope will make a lot of sense to us. It's just like, all right, we're assuming under the null hypothesis that the distributions were the same. It did not matter whether the women smoked or did not smoke in that universe, right? It did not matter. And so in that case, we could just kind of throw away which label went to which mother, couldn't we? If there really was no difference between the values for smoking women and non-smoking women and how that influenced the birth weight, then if we were to shuffle those labels, the trues and falses, if we were to send them to different babies, that would make us a universe where, like, it didn't matter. That would give us another sample, wouldn't it? Does that kind of make sense? It's like, it didn't matter. Like, that, this birth weight could have gone, like, it was maternal smoker true, this birth weight could have just as easily gone with another one of the false ones. Like if I were to shuffle all of these and attach a birth weight to the shuffled values, that would be me simulating a universe where these facts did not matter. Does that make sense? It's a similar idea to that like midterm example, but it's from a different perspective. So I like this perspective a lot. So shuffling labels shouldn't make a difference. If the null hypothesis is true, then any rearrangement of our labels should be equally likely. We do have to play the game of like we had exactly in our sample, or in our original sample, we had 715 non-smoking women. We had 459 smoking women. We can't just go make up like new values. We have to keep it 715 falses. We have to keep it 459 trues. Like that's important. But the order of them is what we're going to mess around with. Like it didn't matter. Like you got that many. Like it didn't matter which weight that was attached to under the null hypothesis. Does that make sense to us? Did not matter. If our null hypothesis was true, I could shuffle those. It didn't matter. The weight did not depend on it. Okay? And that's what we can simulate. That's really cool, I think. I like that. So this gives us a plan now. So what we're going to do is we're going to shuffle all of these group labels. We're going to take this column out, all these falses and trues. We're going to permute it. We're going to shuffle it. And then we're going to shove it right back into the table and have those shuffled labels attached to a birth weight. Okay? And we could do that a bunch of times, and that would generate new universes where different combinations were at play there. And we can, again, test this and see, like, all right, under that new generated sample where we assume the null hypothesis is true, how does the birth weight average of the smoking women compare to the birth weight average of the non-smoking women? Okay? That's what we want. It's going to be slightly difficult, but that's the goal. All right. So that kind of shuffling and reattaching is what we're going to do, and we can do that a bunch of times. All right. The word for that, the fancy word for that, if you're shuffling around values, it's called permuting it in statistics land. So what we're really doing right now is performing what's called a permutation test. That's what we're going to do. All right. So take each shuffle label, give it a birth weight, and then find the difference between that new shuffled label average for the new shuffled groups. Okay, does the idea make a little bit of sense? That's the goal. Here's an interesting, like I stole this from the book, but like here's a picture form of what's about to happen. Like I've got all this original data of smoking versus non-smoking labels and birth weights, and what I'm just going to do is like, boop, I'm going to shuffle these things around. Like some of them are going to go to different babies. And so like I'm going to get a bunch of different samples where these things have been shuffled. That is my goal now. Okay? That's where I'm going. So let me do that now. It's going to be, I think this is a cool way to test a hypothesis. Makes a lot of sense. So we're always going back to our statistic, right? This is the value we want to calculate every time we do another like sample and simulate our null hypothesis. So we want group B, so smoking babies, minus group A, the average weight of babies among the mothers who did not smoke. So yeah, let's calculate this for our original sample. Let's get what that number is first of all. And so what's the way that we can do that? We can do the grouping, right? And do the grouping and then like pick out those numbers. So we can start there. So like if I have this, I'll call that, I don't know, call that my means, their averages. Another word for that is mean. The means table. So I got that, and then I can access pieces of it now that I've given it a name. So it's the actual averages, the means, are means table column, not 0 but 1. I don't want to type it out. Like there's the array. I just want to take, it's going to be B versus A, and so this is group B. It's the second thing, the trues, right? So B minus A. So I'm going to take this and subtract from it this. So the way we can do that is like those are the means. Those are the actual averages. And I want to just take means.item 1 and subtract means.item 0 from it. And so that is my statistic for the actual sample. There is a difference of almost 10 ounces, 9 and some change ounces, all right, in the negative direction. Okay, so that's the number associated with our statistic for the actual original sample, all right? And so we're going to simulate and see how, like if it ever gets here or maybe it gets closer to 0. So we'll see. That'll tell us whether the null or the alternative was a better idea. So this is called our observed difference. Observed difference. Whee. And so there's that number. We can save it away. We can compare to it later. Okay. So, okay. What we would like to do is that shuffling that, let's see. How do I want to do this? The shuffling, the reattaching, and then getting the averages. Oh, goodness. Let's just do it once and then we can try to repeat it. It's gonna look a little weird. So first of all, I've got my table, right? I've got my smoking and birth weight table. And I want to shuffle this first column, okay? So one way to do it is to take a sample. You could either do, there's two ways, right? We are very familiar. You can do it the NP way or the table way. Two options. We have np.random.choice. Can do that with the same size, or we can do dot sample on our table. Dot sample. Either way, you guys kind of 50-50 chose each one on the midterm, which was interesting to me. I like that. So where's dot sample? There it is. So you could also just sample and that will give you back rows. You can pick out a column after that's done though. So, okay, here is our goal. We would like to shuffle the labels. So let's get a sample of all the values, right? All the values in this table. We want every single one of them. And we'd like to not do it with replacement. We want the same numbers of falses and trues. Does that make sense? The same exact numbers, so we have to do it without replacing anything. Keep exactly the same amounts in our table. So with replacement equals false. Don't pretend that there were any more or any less smoking versus non-smoking women. We got to keep those numbers exactly the same, otherwise it wouldn't be a similar kind of sample. All right. So we're going to say, what was the size of this table? Smoking and birth weight dot num rows with replacement equals false. That's one way to do it. And then this is a shuffled table where like it's just babies all over again, but the order of them is different. So if I take this new shuffled column out, that's a different order. Does that make sense? Like that's how that could work. If you would like a shuffled sample of the same number of things that you've got, you actually don't have to say, like, give it a size. Dot num rows is not really necessary. You could have said nothing. So does that say that anywhere here? It does not. Does it say that anywhere here? Because that's useful. By default, n equals the table.num rows. So cool. If we did not give a value for the number of rows that we want a sample of, it would just have worked. So I could have said this. So give me a sample of the table of the same number of rows with replacement equals false. So don't like duplicate any falses or trues or any babies. Like keep them all the same. And so now this is a shuffled order of all of the rows of the table. Okay. And if I pick out now just the 0th column called maternal smoker, that's a new arrangement of these labels. All right. So that will work for me. So shuffled. If I take this and I get dot column 0 on that, these are some shuffled labels, and it's going to be different every time. Does that make sense? That's how I can do that. So I'll call that shuffled labels. And then I want to attach it to the original table. So I've got the original table, smoking and birth weight, right? It looks like that. I want to add a new column to it. So like with a column, that is the shuffled labels. So that is, I called it, these are all singular label names, so I'll call it shuffled label. And what I want to do is attach the shuffled labels array to that. And so there's a new table. Do you see that sometimes the false and the true disagree? Like these are the new, I'm going to attach these values to these birth weights now. If I rerun it, it gives me a new kind of sample, so it's different each time. Which is fun. So that's kind of what I want here. I'll call this original and shuffled. I just want to do this a bunch of times. If I would like, I can extract just these two now because I don't really care about the original ones anymore. Just like have this be associated with this now. So I can extract and do a select out the things I care about and be like original and shuffled dot select, give me the birth weight, and then give me the shuffled label. Something like that. just to give me that one. And that can be called like shuffled only. Eventually we're going to do this in a loop. And then once I have that, I can do a grouping, right? I can do a grouping on the shuffled label now. It's not called maternal smoker anymore. It's called shuffled label. Does that make sense? That's what I want. So shuffled only dot group on shuffled label and do np.average on it. There. And that's a much smaller number. It's a much smaller difference between. So due to random chance, like if we assume things happen due to random chance, it looks like this time for this shuffling, the birth weights of the smoking versus non-smoking babies, the difference was very small. It's not 10, it's like 2. That's interesting. That, I don't know. What does that mean? We'll find out, okay? So are there any questions about how I generated these values? Like I shuffled the labels, reattached to the table, and then I took the average after we did the shuffling. Like this is us simulating the universe where the null hypothesis was true. Like what could have happened if I got a rearrangement of smoking versus not smoking? Bless you. So if we're good, I think that's what we want. We would like to come up with a way to calculate these numbers very quickly. I'll call this shuffled group means again. Because what I'd really like is a function to give me this value of this statistic, right? B minus A for everybody. So let's figure that out. I want to be able to do it just as easily for our original table as well as for when I shuffle stuff. So sometimes I'm going to group by a thing called shuffled label. Sometimes I'm going to group by a column called maternal smoker, right? If you're using the original one. So to get our statistic value, our test statistic value, we can make a function for that. So it's called, at least what your book likes to call it, is difference of means. And it's give me a table, call it table, and give me a label for a group, because sometimes it was the shuffled one, sometimes it was the original one, depending on what you're trying to do right now. So give me a label to group by, and then here is what we can do. We can take that table, and essentially do all of this all over again. Select out the things we care about with birth weight included. So where is that? We can do, it's essentially something like this. Boop. And then we're going to do a subtraction as well. It's like the items involving like this kind of thing. Whee. Like it's this kind of process. All right. So we're going to try to combine those in the right way. We're not quite ready yet, but we'll get there. So like this was a table just with the stuff we cared about. So we'll call this, I don't know, it was a reduced table. So it's birth weight from whatever table we were given, right? Whatever table we were given, grouping by whatever label we were asked to group by. So we're trying to generalize everything we just did right now, all right? Take your table, group by that group, and then we want to give the averages, right? We want to group by that reduced group table. We take that, group by, again, the group label. Sometimes it was maternal smoker, sometimes it was the shuffled label is what we called it. Do the average, give me those means. There's the means themselves, here's the observed difference, and then return that observed difference. Something like that is going to give us what we want for each of the things we have. So like here I made a table called, what was it? Original and shuffled. I could run this on both of those now, because it's like, do difference of means on that table, and then give me this difference for the original one. Maternal smoker was its name. That was our original statistic. And then do it for the shuffled label column. Oh shoot, what have I done wrong? Original and shuffled label. Select birth weight group label. Oh, sorry, I say means table here. This has got to be shuffle group means. That's the one. So you gotta use what you just created, excuse me. Using group to generate this, and using this to generate the means. That should be right. There we go. So that now we can call it in different ways to very quickly get that number that we cared about. Does that make enough sense to us? It took like some generalization of what we had done before, but that will give us a number depending on very quickly based on our shuffling. Because now we just do it a bunch of times, really. That is the goal now. Let's make this happen. So let's make a function that does all this process. Do the shuffling, do the reattaching, and give me a value. Give me a difference of means value. That's my statistic. I want to get a bunch of those because I'm simulating the world where the null hypothesis is true and seeing how likely it would be that I found a value that was this small, right? If that was due to chance, I would see a value that small very often, okay? So let's make it happen. So I'll call it, I want to get one simulation, one simulated difference of these means, kind of. So I'll just be very wordy today. One simulated difference of means, something like that. And so just like do it. You don't need to give me anything. I'll make it happen, okay? So I want to do the shuffling, do the reattaching. It's kind of like this process, right? Give me the shuffled labels, make a table. It'll all work out. So shuffled labels is that. And then, so this first part gives me an array of shuffled labels. Then I want to make a table that has that new one attached to it. We could, if we wanted to, not include the original stuff, I guess. We can call it shuffled table. We can be like, all right, give me that, add this column for sure. We don't even need the other maternal smoker one. We just want the, let's see, we want the birth weight, right? I'm sure that actually, honestly, this is fine. Original and shuffled, we can put it there. This is the table with birth weights and shuffled labels. We call that original and shuffled. And then, now that I have that, I can take a difference of means on that table with the shuffled label. So that's this process all over again. It's just doing it all over, one at a time. And I want to return this value. Whatever that gives me back, that's my final answer. So that's going to perform a shuffling, a reattaching of the label, call it shuffled label, and then give me my statistic. So I'm simulating a universe where it didn't matter if you were a smoker or non-smoker. Like the birth weight could have gone with any baby. And if I call this, sometimes I'll get values that are positive, sometimes they'll be negative. It looks like when I recall it a bunch of times, I'm not getting values much bigger than like 1.5 or negative 1.5. Does that make sense what I've done? It was a big process. So like under this assumption, like under a universe where this is true, like we're assuming the null hypothesis is true, we need to be shown that it's not true. We're doing our test right now. We're generating these numbers with a bunch of simulated values under the null hypothesis. We're going to assume that, all right, it didn't really matter if you're a smoker or non-smoker. That birth weight could have been attached to any baby. So we did that. We did the shuffling. We attached the shuffle label to each birth weight, pretending it didn't matter, just like the null hypothesis is assuming. Then we're taking that difference, that special value right here, and we're just going to calculate a bunch of those and see how often it is the case do we ever see a number that is this far away. Does that make sense? That is our test. All right, it's a lot of words, a lot of explanation, but I think we're ready. I'll just do this in a loop a bunch of times now, just like we did last chapter. All right, so I just wanted a bunch of differences, right? Differences equals, give me a brand new array. And all right, let's do it a bunch of times. How many times? Do 10,000 times. Let's do, I guess, in this example, your book did it 5,000 times. That's still good enough. Repetitions equals 5,000-ish. And yeah, let's take a look. So for I in np.a range, the number of repetitions, and you could change this very quickly if you wanted to do more or less. What we want is we want to call this function that many times. So we're going to call one simulated difference of means, get that value, and attach it to this differences array. Yeah, with np.append. take what was ever in differences, add this new value that I get by calling my function that I just made for this specific purpose of assuming the null hypothesis is true and generating a new sample and giving me and simulating that and getting a value back. So that gives me, after I append, it gives me a new longer array that I can shove right back into the differences array. Oops. Differences, and that's pretty much it. Then I get a big long table or a big long array called differences that's been filled in, and we can see what's there. Whee. And this is going to be very similar to what we've done before. So once this finishes, we'll look at the value. So please try it yourself as well. But I'm just going to wait on this star to complete. Question, yeah?
Why is it not adding a ton of new columns called the shuffled labels?
Oh, you think that...
Every time you rerun it, isn't it just adding another shuffled label column? Or...
That is true, but we're always attaching it to our original table. So like this one called smoking and birth weight always just looks like this. We never reassigned to smoking and birth weight. Does that make sense? Yeah. If you reassigned every time you added a new column, then you just keep on adding more columns with the same name. I don't even know if that's allowed, actually. I never tried it. It might give you an error. It's like, oh, I already have a column called that. But that is, yeah, because we're never overwriting it. We're always generating a new table, like with column generates a new table for us. And that's why it's not overlapping. Yeah. Oh man, okay, this is why we did 5,000, because it takes so long. Gotta do a lot of stuff. So while I'm waiting on this, let's, so you try it too, probably. If you're doing it on the big computers, maybe it's faster, I don't know. Here's my question. You try it too, and I'll come around and help you. But, oh cool, nice. There it is, we got some values. Great. You do it too, and here's your crushed dice now. So this is very similar to exactly what we were doing last chapter. So try to generate a histogram now of these differences. And remember that we're trying to compare against this -9 value. Like, we want to see how often do we get that original observed, what do we call it, right? Observed difference, I think is what it was. Where was it? It was after we did this. Yeah, this observed difference. That's the statistic we care about. How often did it ever get that small? All right. Generate a histogram of these differences and compare it to our observed difference. Generate a p-value if you can. That would be a great idea, I think. Okay, so yeah, see if you can try this. I'll leave all of this stuff on the screen. I think that is what we want here. Let me know if you need to see anything else, but I want you to try to make a histogram yourself, just to prove to yourself that you can. Because that's the end of the test, more or less, right? You can see, like, how often did it get that small, this -9 value, right? Because we're simulating a world where the null hypothesis is true. If it was true, do I sometimes see -9? Does it get to be that small? How often? How often did I simulate -9 in each value? Because that would give me a p-value. Try that in a few minutes, and then I'll do it for you. Because that's it. That's your test, isn't it? If you get a very small p-value, it's like that's very unlikely. Very unlikely to ever see that. Due to random chance, which would tell us that, okay, maybe the null hypothesis was not true. I'll give you like a 3-minute head start. should.
Scroll to the difference in means.
Yeah, I also assume we would want that. I wish I could zoom out, that would be helpful. There's that one. Yeah, for the loop stuff, you can also look back to last chapter. Yeah. Give you a few more seconds to try, because I know it takes a while to do the simulation. All right. Let's try it. Let's make a little histogram. It's gonna be, well, I need to make a table then with these differences in it, because then I need to make a histogram out of that table. So table, give me a blank table and add a single column, please, with column. I'll call it, I don't know, difference between group means, and means is just another way of saying averages. And those are my differences. Go there, please. And so then I get this table with all these differences that we've generated, assuming the null hypothesis is correct. Give me a histogram out of those with the default number of bins. And there's kind of the table. If you want to make it fancy, you could be, you can change the title of it using this PLT variable. Gives you the plot itself. And be like, all right, PLT.title. I'll give me the, what do I want to call this? The prediction under the null hypothesis. And so our observed difference value, if we've forgotten what that was, we can say, put it right here, observed difference. Or maybe we can print it like print, observed difference. If you put commas between your print calls values, it will print multiple things at once. It's like observed difference is this, -9. Do we see -9 anywhere on this graph? We do not. And so it's very, very unlikely for us to simulate it under the null hypothesis, assuming that's correct. It's very, very unlikely then to ever see this due to random chance, due to assuming that, oh, there really wasn't a difference in birth weights among mothers who smoked and mothers who did not smoke. And if we want a number associated with that, we can go to a p-value now. Just like how many times did we get a value so small, like -9, or a value even smaller, right? Because a value in this direction would give us even more proof that, oh yeah, there was a bigger difference, right? There was a bigger difference. The difference was smaller indeed. So a number that was this or even smaller, how many times did we predict that? Did we generate that? That's our empirical p-value. So it's give me our differences. How many times was it equal to the observed difference? Probably never. But how many times was it that or even smaller in the direction that would favor our alternative hypothesis? We can count non-zero. np.count non-zero. How many times did that happen? And it's 0. 5,000 simulations that we never saw something that small. If you did like 1 billion simulations, you might get 1 or 2, maybe. It is possible, but it's very, very unlikely. All right, that's the idea. So do that. If you want an actual percentage, you got to divide by the number of repetitions. Like how many times out of 5,000? Is that the thing? That's our empirical p. We can call that our empirical p-value. So we ran our simulation. So assuming the null hypothesis was true, there is a 0% chance you would see a value that small. That's kind of what we've just generated. Does that make sense to us? And so, finally, our conclusion now is, given what we just said, we can conclude then that our null hypothesis is a bad way of viewing this data. It is not very true. We've simulated universes where this is true. We never saw a value so small. So that means that the null hypothesis is probably wrong, and our alternative is a better one. So in the population, the babies of the mothers who smoked, they do way less on average compared to babies among the mothers who did not smoke. Ta-da! So that took a lot of words and trials, but we got there. Any questions about how we were able to conclude that and calculate these values and these p-values and these differences? Does that all make enough sense? It's kind of fun. It's like having this new way to test things. The shuffling makes sense to me. It's like, all right, yeah. If it didn't matter, it could have been in any order. I like that so much. So we have a lot of different ways now to test a bunch of different hypotheses. And so probably, yeah. What we should do now is I've made a little cheat sheet for us. I stole this from the book. But we have a bunch of different ways that we might formulate a question, and we have a bunch of different ways to do the testing now. So let's remember all the different ways, because I will eventually use sample proportions again. Let's not forget about that. So sometimes we've took one sample of a bunch of things, and there are 2 categories of things we care about in that sample. That was like, think back to Mendel, however you pronounce it. So that's like, you've got a bunch of flowers, and some of them are purple and some of them are white, and I've taken one sample. I've got my garden only. Okay, so for that one, like, how do you want to see, like, what is the proportion, what I think it should be, right? What is the proportion? What is it, what I think it should be? Is it really a 75-25 split, even though I saw something different to that? Okay, and so your statistic that you calculate as you're doing your simulations could be a bunch of different things. It could just be the proportion of the purple flowers that you saw. It could be the difference, how far away was that proportion from what you assume it should be, like 75% exactly. Take the absolute value, we did something like that. But if you want to do a simulation under your null hypothesis, like there was an exact 75-25% split between these 2 categories, this is what we did, right? So you can come back to these 2 slides to see all that. I've colored them green for fun. So you can do sample proportions with the exact same number of plants or whatever your sample is from, and you have a distribution, 75-25, that's what we assumed. Okay, something like that. So that's that one. Yell at me if you have any questions. I'm just reminding you of all these different ways we know to test things. Sometimes you have a sample, but you have more than 2 categories of things. It's like you've got a sample of jurors, right? A bunch of jurors, and you have ethnicities. There's more than just 2, of course. So what we found is there is a way to generate different samples of like proportions of juror ethnicities, and because you have a bunch at once and you want to compare them to like the one that we saw in practice or the one that we think it should be, that like corresponds to the proportions of the ethnicities in the county or whatever, we called that the total variation difference. Total variation distance, excuse me. And so you can go back to that, and like you can compare your distribution with another one. It's like it was supposed to be these values in this order, and you got some other values in like this other weird order, but you still got 4 and 4, and like you can do a value comparison. right? So there's that. And again, it would be sample proportions. It's like, this is what I think the distribution is. Like, this is what the county's population is of eligible voters or eligible jurors for all these different ethnicities. I want just the same as we saw in the study. Give me these values and I can generate a bunch of test statistics. All right. So that's if you have a bunch of categories, but just again, a single sample of like all the jurors from the past year. So remember those? So that's those. Then we also have, maybe you have one sample, but you got some numerical data. So like you have a sample of all the test scores for the midterm groups of like the people who took a midterm versus the lab section that they were in. So it's still one sample of all your people, and you want to test like, was this one section worse off than all the others? And so what we determined was like, you can, what's the number that we could use to see how far away it was, or like how often this would happen if there really wasn't a difference. You can just like generate a new lab section randomly, get a mean, or maybe you could take, you always have options. I think we took this one. You could also have taken like, what's the distance away from what I think the mean should have been. It's like, this is the average of everybody or something. Like, how far away was it from that? Something like that. And again, to simulate, now it's not sample proportions. It's like, you've got this data, you've got exactly this many students in this lab section. Give me another lab section of that exact size out of everybody, because the section that they were in wasn't supposed to matter. So this is very similar to it's called the permutation test stuff that we were doing today. It's just we called it something different. That's one sample numerical data. And then the new stuff from today was we had a couple samples. We have 2 numerical samples, and we're not sure. We want to know, did those samples come from the same distribution deep down? So that was our A/B testing. That was our smoking example. And so you can, again, you have to generate a number, right? You're going to simulate your null hypothesis. You're going to generate a number for each simulation to give you firepower either towards the null or towards the alternative. And so you could do some subtractions. You can do A minus B, you can do B minus A. Sometimes the absolute difference away from each other is fine if you're just trying to say, like, was it 0 or was it non-zero? Were they close together? Were they not close together? That's fine. We cared about a specific direction, like the children of the smoking mothers were, in fact, they weighed less, and we cared about that direction only. So that's important. But yeah, to simulate again, you want to shuffle. So you're going to take a sample of the exact same number of everybody now in all of your groups. So you just don't give a number. You say with replacement equals false again to make sure you have the same amount, because you had like a certain number of smokers, a certain number of non-smoking mothers. You want to keep that same number, but shuffle them around. All right. But yeah, your statistics, these numbers that you're calculating as you're generating your simulations, they could have been anything. They could have been any number that made sense to you. You do have options there. Yeah, these are things that you can come back to as you're studying for maybe the final or something. But like those are all the different ways we know how to test stuff, kind of. But yeah, we did this last one just now. Okay, that's what just happened. Yeah, I think that is more or less the smoking example. I have one last thing to kind of say about it. Are there any questions before I go there? So, because I want to go back to correlation versus causation, which is the age-old question. Are you ready for that? All right. So the goal now, like we have a value. We know that it's very, very unlikely for this to ever have happened, right? The smoking, the babies among the mothers who smoked, they for sure weighed less. That was not just due to random chance. And now the question is, was smoking the cause of the weight difference, right? That is, we can't immediately say that, all right? And let me tell you why. So it could have been the cause, or there was some other confounding variable. There was something else involved that all the mothers who smoked, they had to deal with, and all the mothers who didn't smoke, they didn't usually have to deal with that problem. So that's called a confounding variable. It's something that's confusing us and making us think one thing, but it's not. So there's a couple problems with thinking that smoking was the cause, even though it probably was. It was probably a very good cause. We don't know from this sample because, first of all, it was the mother's choice whether to smoke or to not smoke first. Yeah, right? We didn't just take a bunch of random women and be like, you're going to smoke for the duration of your pregnancy. You're not going to. That would be unethical. That would be horrible. And so it was not even a normal sample. It was like a sample of convenience, if you remember that word. It's like we we got what we got, and we had to go with that data that we received. All right. So we have shown an association between smoking and birth weight. We have not shown a cause because we don't have like a random sample. First of all, does that make sense to us? That's important. If we did really do that, if we were very unethical, we like forced women who were pregnant to smoke, we got some random samples of women, we split them randomly into two groups, then we could totally say causation. All right, that's called a randomized controlled experiment. Usually you think of it in terms of drugs, but it could be anything. That's where you have a control group, somebody who does not get a treatment, and then a treatment group where somebody does get a treatment. It's like treatment group is like the mothers who were telling to smoke. The control group is the mothers were telling to not smoke. If we were to have done that, then we could for sure say causation. Does that make sense? If we were to do that. That would be very unethical, though. We would never do that in real life. So that's the thing. If you did it that way, though, if the treatment and control groups were selected at random, very, very important, then you could totally make causal conclusions. This word always makes me think it says casual, but no, it's missing an S. It's causal. It has to do with cause. One caused the other, right? So drug trials are a great example of that. And yeah, so we're not sure. It's probably likely, very likely, that smoking causes birth weight differences. But for this particular sample, we do not know. All right, we cannot say causation because if you think about it, like I don't know, I'm just gonna spitball here, but like if you are a woman and you smoke during pregnancy, it's probably very likely that you are less educated. Because I think we go to school and we learn that you're not supposed to do that. You're probably not as well off financially. And so there's a lot of different things that could be involved there, right? That are not just causes, that are not just smoking. It could be like, maybe you don't know, like you're not as well fed even, like you don't have as much to eat. And so your baby's not going to grow as fast. Question?
I was going to say smoking actually increases your metabolism by
Ah.
10%.
Interesting.
So that could be
That makes sense. So yeah, you need to expend more energy, and so that energy can't go to having the baby grow. It has to go to your own body. Thank you. Yeah, that's good to know. So whatever it is, we're never going to do the proper experiment, but we can do this enough times to get a good, maybe a bigger sample would help us confirm that, yeah, maybe there's something wrong with smoking. Mothers shouldn't be smoking. Something like that. So yeah, that's important. But if you were to do this, like for a drug or something, then you can get some really good, you could really prove causality. And this is what they did for example, the COVID vaccine. So like we kind of talked about this before, but it's a good idea to go back to it. It's like, this was the Moderna vaccine. And so you can kind of see what happened. There were two groups. There was a treatment group and a control group. And they were like, all right, you're going to get this. You're not going to get this. And so this on the, what is it? And this is the x-axis, is time, number of days since somebody received, I guess, their first shot or something for the COVID vaccine. And it was, and then on the y-axis is how often people in those groups, like percentage-wise, did they get COVID? Did they test positive for it? Or, yeah, I think it's just positive tests rather than like symptoms or something. And so placebo is the control group. That just means you didn't get the drug. And then the red group was like you got the vaccine. And you could see that the incidence rate like just gets higher and higher for the people who did not get the drug. And it stays pretty nice and level and low for the people who did get it. And so because this was a randomized controlled experiment, they took random people and split them up into these two groups where all of the differences between those people averaged out. Then you could really prove causality. You can say that, oh yes, this vaccine was effective in preventing against COVID symptoms. COVID true tests or whatever. Positive COVID tests. And so yeah, that's the moral of the story. If you want to prove causality, you got to do a randomized controlled experiment. Otherwise, all you got is an association. All right? Questions about that? So yeah, as good data scientists, you need to have that burned into your mind. And so that's why I'm saying it so much. Let's see. Yeah, I think that's more or less what I wanted to say. We'll do a little bit more next time. Maybe we can do this one and maybe not that one. We'll start with that example next time and we can do it together. So yeah, here's one last example of like, you really want to do some random assignment. You want to do a randomized controlled experiment if you want to have anything to say about causality. So here's a silly little graph. Let's read it together. So this was quite a while ago, almost over a decade ago, but I'm sure it still rings kind of true today. But if you go on the Apple App Store, the iOS App Store, or the Google Play Store, there's apps that you can pay for, of course. I have not really paid for many apps in my day, but there's one that I care a lot about that I paid for, at least. Some people, it turns out that people who have iPhones, they end up paying more for apps. That's just something that they collected data on. Like let's see, more people are downloading apps on the Google Play Store. It seems like these are shares. The light blue is Google Play, and the dark blue is Apple App Store. But the percentage of who's spending money, like how much money are the iOS users spending on their apps versus how much money are the Android users spending on their apps, I guess every year. You can see that it's for sure shifted towards Apple. Like more people who own iPhones are spending more money on apps than Android users. And so the question is, if you buy an iPhone, like, is that the cause of you spending more money on apps now? Like, just if you have an iPhone, are you going to just force yourself to spend more money? That's the question. We have no clue, right? The answer is we have no clue. This is just you're surveying people who have already chosen to buy an iPhone versus an Android phone. We have no clue. We didn't randomly assign people in the world. Here, you're going to have this iPhone. Go see if you spend money on it. You're going to have this Android phone. Go see if you spend money on the apps that you want to go download. So it's an association. It's not a cause, right? And if we randomize things, maybe we could prove a cause, but more likely we can't. And again, if I try to think about the differences between iOS users and Android users, Android devices are sold in countries that are less off. It's harder if you like. iPhones are, I guess, they're more expensive. I think they're technically more expensive, and so if you're in a country that does not have where people are not paid very well, you're most likely going to have an Android phone. You're not going to spend as much money on your apps, things like that. So there's a bunch of other confounding variables, right? A bunch of other factors that would tell you whether or not somebody's going to spend money on phone apps. It's like, how much money do they make? There are certain countries that prefer Android phones because they're cheaper. They don't make as much money in that country. Just like where you are in the world. I think in China, for example, like they have a bunch of different manufacturers for Android devices that aren't even sold in the US, and they're just so cool. But we don't get those, but they maybe prefer those, something like that. And maybe all of the apps that they need are free if they're localized in China. Like we don't have those options here, for example. Something like that. I think that's all that I wanted to say. So do you see how you took a survey? It was a sample of convenience again. We have no clue. There are other confounding variables most likely that have to do probably a lot with income that would explain this. Not just like, oh, you bought an iPhone, you're going to force yourself to spend a lot of money now. Okay. Yeah, I think that's all that I wanted to say. That's a good place to stop, I think. Are there any questions before I just set you off to work on things? You good enough? All right, so I'll remember that we stopped there, to be continued. And yeah, I don't have anything new to give you. I'll give you, of course, an assignment after we finish these slides, but next time I just want to do some practice with all this stuff, and we will go from there.